When looking for the angle given the trigonometric function, one just uses inverse trigonometric functions, the derivatives of which have a different pattern. Learn about them here in differential calculus. There are 6 inverse trigo functions too, and a pattern is also observed when taking their derivatives. First, the derivative of arcsine x, or inverse sine x, is u prime upon the root of 1 minus u squared. The derivative of arc cosine x is negative of u prime over the root of 1 minus u squared. The derivative of arctangent of x is u prime all over the quantity of 1 plus u squared. Next is the derivative of arccotangent x, which is negative u prime over the quantity of 1 plus u squared. Then the derivative of arcsecant x is u prime upon the root of u squared minus 1. Lastly, the derivative of arccosecant x is negative of u prime all over the root of u squared minus 1. Notice the pattern that the negative derivatives are again taken from the co-trigo functions. And checking each pair, the first two have the root of 1 minus the square. The second pair has the pattern of 1 plus the square. And the third pair has the root of the square minus 1. Let's start with simple examples like the one with w is equal to arcsine of 4t. As we have just discussed, the derivative of arcsine is u prime upon the root of 1 minus u squared. So from the premise, u is 4t. U prime is taken as 4 times dt all over dt. So u prime is simply 4. U squared, on the other hand, is the square of 4t, which is expanded as 16t squared. So placing u prime and u squared into the pattern, w prime becomes 4 upon the root of 1 minus 16t squared. The second example looks for the derivative of z, which is equal to arctangent of t all over a. From the rules, we take the derivative of arctan x as u prime all over 1 plus u squared. And from the premise, u is t all over a. U prime is solved by differentiating t all over a, and since a is a constant, we can extract it out the derivative, making 1 all over a times the derivative of t all over dt. This is simplified as 1 all over a. U squared is the square of t all over a, or that is t squared all over a squared. Thus, z prime is the reciprocal of a all over 1 plus t squared over a squared. To reduce too many fraction bars, we take the LCD in the denominator. So we have 1 over a all over the ratio of a squared plus t squared upon a squared. From here, we can cancel some a's in the denominators, simplifying the equation into 1 all over the ratio of a squared plus t squared upon a. Flip the denominator a into the numerator to have z prime as a all over a squared plus t squared. Example 3 has the equation of z, which is equal to arc cosine of the quantity 1 plus 4w, and the derivative of arc cosine is negative u prime over the root of 1 minus u squared. Then again, identify u from the premise, that is the quantity of 1 plus 4w. With the binomial, the derivative can be taken separately as the derivative of 1 and the derivative of 4w. The first term is taken as 0 as it takes the derivative of a constant. The second term has 4, so the resulting u prime is 4. Also, the square of u is the square of the quantity of 1 plus 4w. Place the two parameters into the z prime equation to have negative 4 all over the root of 1 minus the square of 1 plus 4w. If we expand the square, we have z prime as 4 all over the root of 1 minus the quantity of 1 plus 8w plus 16w squared. This can then be simplified as 4 over the root of negative 8w minus 16w squared. Next, we can factor out 4 from the denominator, and also take it out from the radical sign to make it 2. This can then be cancelled with the numerator, making z prime as 2 all over the root of negative 2w minus 4w squared. The next example has the equation r is equal to arctangent of the square of s, and the derivative is u prime all over 1 plus u squared. So from the equation, u is s squared and its prime is solved as 2s. U squared is the square of s squared, and that is simplified as s raised to 4. So, r prime is 2s all over 1 plus s raised to 4. The other equation looks similar with the one we just solved, but the square involves even arctangent. This function uses the power rule, as the outermost operation is the exponent 2. So r prime is 2 times arctangent of s times the derivative of arctangent s. At this point, u is s and u prime is 1. Also, u squared is s squared. So r prime comes as 2 arctangent of s times the reciprocal of 1 plus s squared. Example 6 has the equation s is equal to t squared times arcsine of t. This function involves two terms again. Those are t squared and arcsine of t. By product rule, that is u dv plus v du, we get s prime as t squared times the derivative of arcsine of t plus arcsine of t times the derivative of t squared. The first derivative requires inverse trigo, and the latter term is power rule. For the inverse trigo, we identify u as t, and its u prime is taken as 1. U squared is t squared. Plug them into the s prime equation to have t squared times the reciprocal of the root of 1 minus t squared plus arcsine of t times 2t multiplied by dt all over dt, which is 1. We can simplify then s prime as t squared over the root of 1 plus t squared plus 2t times arcsine of t. With one term having a denominator, take the LCD, making s prime as the numerator, t squared plus 2t arcsine of t multiplied by the root of 1 plus t squared over the denominator, the root of 1 plus t squared. With the radical sign in the denominator, we rationalize to take it out, so we multiply the whole s prime equation by the root of 1 plus t squared on both numerator and denominator. So the denominator will be 1 plus t squared. The root is then distributed among the terms in the numerator. With a little arrangement, we get the final s prime as t squared times the root of 1 plus t squared plus 2t times the quantity of 1 plus t squared. and again multiplied by arcsine of t. Everything is over 1 plus t squared. Example 7 involves the function w is equal to twice of arcsine of the root of v all over 2. The derivative of arcsine x is u prime all over the root of 1 minus u squared. So from the premise, u is the root of v all over 2, which can also be written as v all over 2 raised to 1/2. U prime is taken as half of v all over 2 raised to negative 1/2 times the derivative of v all over 2, which is 1/2 times dv all over dv. So u prime is simplified as the reciprocal of 4 times the root of v all over 2. U squared is also taken as v all over 2. Plugging them into the main prime equation, we have w prime as 1 upon 4 root of v all over 2 divided by v all over 2, where 4 and 2 are cancelled, reducing w prime as 1 all over 2v times the root of v all over 2. If we distribute the radical sign in the denominator, we get 2v times the root of v all over the root of 2. This time, flip the denominator root of 2 into the numerator, and also to place v's into a single variable to have w prime as the root of 2 all over 2, the root of v cubed. Again, with the radical sign in the denominator, we rationalize by multiplying root of v cubed. Thus, the final w prime equation turns out as the root of 2v cubed all over 2v cubed.